So we're going to look at an introduction to the topic called roots of unity. And this is sort of tying together our knowledge of complex numbers, how to take the cube root or the fourth root or the fifth root, and also a little bit about the geometry. So we need to visualize what's going on with these questions as well. Okay. We'll start with an example, so it'll be easy to see with an actual example instead of doing it in terms of n. So the first one says, solve set to the 5 equals 1. And clearly if we get an equation like this, set to the 5 equals 1, we should be able to see straight away, well, we know one solution. There's a real solution, which is the number 1. Okay. But if you wanted to follow the method, just while we get used to this, before we take the fifth root, we can write it in exponential form. So that would be the same as 1 e to the 0 I plus 2 pi ni. And then when we do take the fifth root, we raise it all to the power of 1/5. We've still got 1. And this would be 2 pi over 5 ni. And obviously now we could let n equal, we're looking for 5 roots, so 0, 1, up to 4. And that will give us our 5 different roots. But I mean, there's an argument that when you get used to this topic, you'd actually know what these roots are without doing this bit of algebra. Okay? If you think about the Argon diagram, I'll attempt to draw a circle. I've drawn worse. All of the roots of this equation are going to lie around this circle of radius 1 in the complex plane. So the first root would be 1. The second root would be, if we sub 1 in, we'd get e to 2 pi over 5 I. Now if you think about it, there are 5 roots to this equation. One full circle is 2 pi. 2 pi over 5. And we're splitting the circle up into fifths. Okay? And there are going to be 5 solutions along this circle, which are evenly spaced out. And they're actually going to give us a pentagon. Okay? So 2 pi over 5 would be around about here. And the first complex root in this topic we denote with the letter omega, lowercase omega. It looks like a W, but it's not an omega. Okay. The next root would be another 2 pi over 5 along, which would be e to the 4 pi. Over 5. The next root, and think about the symmetry of this. If it's 4 pi over 5, the next root would be e to the 6 pi over 5. Now 6 pi over 5, don't forget, is, if I draw this line on, again, please use a protractor and a compass because it'll be more accurate. 4/5, think about the line itself is pi, so if we've got 4/5, that would be 4/5 of pi, and that's 1/5 of pi. It might not be exactly to scale my one, but that'd be 1/5 of pi there. 6/5 would be another 1/5 that way. So 6 pi over 5 is the same as minus 4 pi over 5, and that's important that you illustrate this because 4 pi over 5 that way, minus 4 pi over 5 this way, these two solutions should lie in the same sort of, if you imagine a vertical line, they should lie on the same vertical line. And if you were asked to sketch this, you would need to represent that symmetry in your diagram. And the last one, I'm slightly out of not very accurate here, am I? But the last one would be below this one. And that's if we turn another 2 pi over 5. So again, it would be e to the 8 pi over 5 when we let n equal 4. But 8 pi over 5 is the same as minus 2 pi over 5. So this angle here would be the same as this angle here. Let's try and get a little bit more accurate. We should be directly below this one. Okay. Now this first example is a bit more of an investigation than an exam style question, because like once we've drawn the 5 roots on, it then asks us if omega represents the first complex root. So if this one's omega, what would omega squared be? What would omega cubed be? So if I say, well, omega equals e to the 2 pi over 5, can we see that omega squared, if we square this, would be the same as e to the 4 pi over 5i. In other words, there's our first real root, our first complex root, we call omega. The next root here would be omega squared. And if we cube it, we'd get to this one, which would be omega cubed. And if we raise it to the power 4, we'd be here. So this would be omega to the power 4. And if you did want to raise it to the power 5, well, omega to the power 5 would equal 1, because, like, think about it, omega is a root of this equation. A root of this equation, we know omega is one of those roots. And if you raise that to the power 5, it solves the equation, you're back at 1, aren't you? Okay? So, there's a couple of ways that you can ask this question in the exam, but the one thing you've got to bear in mind is it will link in with the geometry of the situation. So if you're solving the roots of unity, which means the roots of 1, so like the 5th root or the 3rd roots, they will all lie evenly spaced out along this circle of radius 1. And the first root will always be the number 1, and the first complex root we will call omega, and then omega squared would take me to the next one, omega cubed would take me to the next one, and so on. Okay? The last part of this question is going to help us with some exam questions, because this is another like very common sort of theme that comes up on these questions. If we're being asked about 1 plus omega squared plus omega cubed plus omega to the 4, and we're asked to solve when does that equal 0, essentially we're working with a quartic equation, and we're trying to find the roots of a quartic. Before we jump straight into this, let's just take a step back and think about what we've just solved. So if you look at z to the 5 equals 1, we know there's 5 roots of that equation. 1 e to the 2 pi over 5i, and so on, all the way up to e to the 8 pi over 5i. So we've got 5 roots for this equation, but look, let's just focus on the real root for a second. If 1 is a root of this equation, let me just rearrange this. So if we think about this equation instead as a polynomial, and if I was trying to find the roots of the polynomial, if I know 1 is a root, I also know a factor of this polynomial. I know that I can write this as z minus 1 multiplied by some other stuff. Okay? So this equation here we can rearrange. We know the real root is 1, so we know z minus 1 is a factor. Now it just so happens that that stuff that we've got left here will be 1 plus z squared plus z cubed plus z to the 4. I'll show you where this comes from, because obviously we wouldn't be expected to just jump from that line to that line. Okay, but just bear in mind that this equation has 5 roots. The real root is z equals 1, and the other 4 roots are going to be the roots for this bit that we're being asked about. But let's just think about, well, how can we go from this line to this line, instead of me just assuming that we could factorise this. Okay, so one way of doing it, which I wouldn't recommend in the exam, but one way is just to do a division. Like if you've got z to the 5 minus 1, you could set it out as a big algebraic division. Z to the 5 divided by Z would be Z to the 4, multiply, subtract, and then you get Z to the 4. Z to the 4 divided by Z would be Z cubed, and you'll see that you'll end up with Z to the 4, Z cubed, Z squared, and so on. But probably a neater way of thinking about it, and then actually considering what's going to come next, like the next topic, a better way of thinking about this is if we focus on this actual question that we're being asked about. 1 plus omega squared plus omega cubed plus omega to the 4. Now if you focus on this expression, that's a geometric sequence. We could say, well, the first term in my sequence is 1 and the common ratio is omega, because I'm multiplying by omega each time. And what we're being asked about here is equivalent to the sum of the first 5 terms of a geometric sequence. So we could use the sum formula. It's A 1 minus R to the power of n, all divided by 1 minus R. So without having to do that big algebraic division, look at this summation here, and we can say it's equivalent to this. In other words, 1 plus omega squared plus omega cubed plus omega to the 4 would be the same as, now I'm just going to, because this is 1 minus and 1 minus, I'm just going to multiply the top and bottom by minus 1, because that would be equivalent to omega to the 5 minus 1 divided by omega minus 1. Can we see the link? So I know this thing I'm being asked about, this geometric sequence, is the same as omega to the 5 minus 1 divided by omega minus 1. In other words, if I multiply up by omega minus 1, I'm back at this. We know that omega to the 5 minus 1 is the same as omega minus 1 multiplied by this, 1 plus omega squared plus omega cubed plus omega to the 4. Okay, so it may, if it asks you about this in the exam, it may ask you to justify the link between this expression and then this factorized form. And I would probably do it as a geometric sequence. So once we've realised that this equation that we started off with is the same as this polynomial, which is the same as these two things, we now already know that there are 5 roots of this equation, 5 roots of this equation, 5 roots of this equation. 1 is our real root. We're being asked about the roots of this. So this is equivalent to 1 plus omega squared. And the roots of this are the 4 other roots. So the roots would be e to the 2 pi over 5i, e to the 4 pi over 5i, e to the 6 pi over 5i, and e to the 8th pi over 5i. If you wanted to, you could substitute one of these into this equation and square it, cube it, and convert it back from exponential form, and you will solve the equation. It will be equal to 0. Okay, it's fairly heavy on the sort of the conceptual ideas behind this topic, isn't there? There's a lot going on. It's like this, the geometry, the question, the link between the different roots. But there's a lot of exam questions on this topic that we can practice. Okay, thanks guys.